raise your hand or write in the chat and we will take care of them. So recording has started. And today we have Itai Shufaro who is giving a presentation. And so Itai is a master student at the Technion. He's working under the supervision of Shai Manor. He's a recipient of the Meyer Award. And before that, he obtained his bachelor's degree in electrical engineering and physics from the Technion as well. And his research interests primarily lie in statistics and reinforcement learning. And so I think today is going to tell us about a new kind of like lower bounds. So Itai, thank you for accepting the invitation, and you can start the presentation.
Okay, thank you, Antoine, for introducing me and inviting me to give this talk. So, hello, everyone. Today we're presenting this paper, which is a joint work between me, Nadav, Nir, and my advisor, Shai. The paper has been also been recently accepted to the upcoming iClear. All right. All right. Before we begin discussing the main content of the paper, let's look, for example, at online tasks. So, as you probably all know, in online tasks, we control some agent. For example, in a video game, we control the player here, whose goal is to interact with the environment to maximize some reward signal. For instance, if we look at this video game, we have our agent here, and his goal is to maximize his reward, which is given via feedback, for example, by collecting this key. All right. In order to maximize the reward, we know that the agent must play actions that are good in the manner that they maximize the expected reward that he will receive. On the other hand, in order to discover such good actions, we must explore, potentially suffering regret, because when we play known actions, we'll also play suboptimal ones. And this is the well-known exploration-exploitation trade-off. Okay. Now, in this work, we're more focused on settings where we have external advice. So sometimes we might have advice from external sources. The most recent example can be found in foundation models, in large language models, like GPT, Claude, or Gemini. And for example, in our video game example, we can use GPT to potentially reduce our required exploration, right? If we input this game frame into GPT, it can give us advice, for example, tell us what is the goal of the level, and thus potentially reduce our required exploration, and also reduce the amount of regret we potentially suffer. This hints at some sort of trade-off that exists between information that we have and regret that we will suffer. If we look at this more formally, let's compare between two agents, agent A and agent B. Both agents interact with the same environment. However, we have a key difference between these two agents. Agent A is allowed to play more rounds with the environment, thus he has more experience, but he suffers additional regret. Now, agent B has not yet played any rounds with the environment, so he has no experience. However, he is allowed to query an external knowledge provider, for example, our foundation model, and he is allowed to query information from it as much as he would like. We are interested in the question, how much information does B need in order to catch up with A? So to reach the same level of performance A has now after he has suffered this amount of regret, but by only querying external information. In other words, our objective is quantifying the exact relationship between information and regret. Right? So before we dive deeper into our methods, we'll discuss our setting. So our setting is actually a common Bayesian setting that is general for a wide variety of decision-making tasks. So we assume that this task is defined by the following: a decision space, a model space, and a context space, which represents our external information. some reward distribution function that maps the model, a decision, and the context to a distribution over the line between 0 and 1. So we assume that the rewards are bounded. And observation space O, this is done to make our setting more general. We are not limited to only receive our reward as feedback. We can receive general observations. The observations and the rewards are sampled from some joint distribution function. And because we assume a Bayesian setting, we assume that you have some joint prior between our model space and context space. Right? Every task in our setting follows a similar structure. So before the agent begins interacting with the task, some model is sampled according to our prior. Then the agent plays the task for T rounds. In every round, the agent receives a context that is also sampled according to the prior. The agent then determines some policy, where the policy is some probability distribution over the decision space. A decision is then sampled according to the agent policy, and the agent is revealed some observation that is received as feedback from the task, and some reward is outputted that is used to measure the agent's performance. And we use the standard Bayesian regret to measure the agent's performance. All right. So for just some short example to show how it covers common decision-making settings. So for example, a contextual multi-armed bandit, we can select a finite decision space, a finite context space. We can determine our reward distribution to be equal to some Bernoulli, that such that the mean is different for every model, decision, and context. And we can select our observations to be equal exactly to the rewards. And then we can select the prior to be some arbitrary number, arbitrary distribution over models. It doesn't really matter. All right. Some other important additional notations that will be useful later on when we reach to the proofs in our paper. So we denote by HT the accumulated history up to step T. We use small p to denote the agent's policy. We denote by I the mutual information of two random variables, and with the KL divergence, the KL divergence of two probability measures. And we denote by like script n with lock, and script n, the packing, local packing, and covering numbers, respectively. All right. We can now state the contributions we made in this work. So our first contribution is introducing a novel method that allows for obtaining regret lower bounds for problems under the setting we showed. We then use this method to derive regret lower bounds under the following information constraint. So the mutual information between the optimal policy and the history is constrained by some positive number R. We then also show regret upper bounds under this constraint as well. And finally, in the last part of the paper, we show how these two bounds quantify the trade-off between information and regret, and we then show how it can be utilized in more practical online tasks. All right. So our lower bound, or more specifically our general method for obtaining lower bounds, is heavily based on Fanon inequality, which we state here. So without diving into it much too deep, let's say we have some two random variables, x and y, that are jointly distributed, and x takes values over some finite set. Fanon inequality essentially lower bounds the error probability when trying to predict x using only the information present in y. All right. Fanon inequality is also widely used for lower bounding the error in hypothesis testing problems. The main question that followed us in this part is how can Fanon inequality be applied to lower bound the regret, or how we can apply it to general regret minimization problems. So before we begin the proof, I just want to state here that yes, we managed to do it, at least initially. We can see here the Bayesian regret term over here. and the lower bound is some Fano-like term. And we achieve this using the following method. All right. So let's consider the worst case Bayesian regret over here. Now, in the regular worst case Bayesian regret, we always compare our performance to the best decision in hindsight, right? We look at every time step at our context and our current model, and we always compare ourselves to the best decision in hindsight. The first step we are trying to do here is we fix some decision set phi, which is finite. And instead of comparing ourselves to the best decision in hindsight, we will compare ourselves to the best decision from this finite set. Okay. We then make the following assumption. We assume that there exists some metric that lower bounds the mean difference. This assumption mainly holds for a lot of online decision-making problems, and it is used later on. We'll see later on why this assumption is useful. Then by using Markov's inequality and additional steps, we see that we can lower bound the Bayesian regret by epsilon t divided by 2 times some probability here that for all time steps, we will always choose a decision pi t that is far by a factor of epsilon by 2 from the decision phi k.
Sorry, can I have a question here?
Yeah.
So maybe you're gonna explain this more later, but can you say something about this assumption? So what is phi and psi here, and what rho is? Maybe I just missed these definitions.
This actually didn't explain it well. So this assumption essentially says that if we have some two stochastic decisions, right? So some two policies, phi and psi, then the mean difference between these two, the mean reward difference in absolute value of these two stochastic decisions can be lower bounded by some metric, which is rho. So right now we did not talk about what rho exactly is, but we assume that it exists.
Right. Okay. So that means that I'm always, so if I'm playing two policies that are different, then I'm always going to be seeing different rewards, essentially.
Yeah.
Okay. So there's not going to be like a non-informative pair of policies.
Yeah. Chava, I also see that you have a question.
Yeah. So like here, the main thing is that this is independent of P, right? Like this rho metric applies no matter what the prior is. So no matter what problem you're in, the metric just like tells you that there will be some loss. and the loss is expressible in terms of what policies are doing.
Yes. Wait, no, sorry. Okay. Did you finish your question or?
Yeah, that was just like a clarification question of whether the main point of this is that this rho is independent of P.
Yeah. And the main point of it.
Otherwise, you can just like define it as, like this expected value, but this would like, you can also define it as the infim of the expected value over all possible P. And then you got a rho, like you always have some rho. There will be a question of like whether that rho is good enough or not, like what property does it need to satisfy. I'm like, it's going to be non-negative, but like, but you also say that it's a metric, right? Like triangle inequality needs to be satisfied or something. And then if I just use the inf over P, is that clear that that's not going to be a metric? Like a sup over P would give me a metric, not an inf.
Yeah, so an inf won't give you a metric, but actually because we focus here on the worst case Bayesian regret, what you can essentially do is look at this worst case Bayesian regret and then look at some subset of priors in this set. The Bayesian regret will still be lower bounded by the supremum over this subset of priors, and then you can still choose an appropriate rho without choosing a sup or inf.
Okay. Yeah. Okay, we'll see, I guess.
Yeah, all right. So here the Bayesian regret is upper bounded essentially by this probability here. And what we're going to do now is turn this probability here to the probability of error in hypothesis testing problems. So it's actually a pretty standard technique. What we're going to do is to consider this. Let's say we have some stochastic decision here, phi I. Now, essentially, if the metric row between pi t and phi I is less than epsilon by 2, we can think about it as we have some sphere here. Using the metric row, we have some sphere around the stochastic decision phi I, and then we ask ourselves, all right, does the decision pi t land inside phi I or not? Now, if we have some other decision phi j, and we assume that the decisions phi I and phi j are epsilon apart away from each other, then we can think about pi t being in the sphere of phi I and not in the sphere of phi j as some sort of a predictor, right? A predictor which selects a decision from our set according to the sphere pi t lands in. All right? So our error in this time, it means that pi t lands outside of the sphere. And in this way, we managed to reduce our problem now to hypothesis testing. So just to state it formally, we had another constraint to our set selection. We selected a decision set phi, such that the metric row between the two decisions is larger than some epsilon. And then the Bayesian regret can be upper bounded by epsilon t divided by 2 times some max inf over a probability error of a finite hypothesis testing problem. Okay, and now that we have an hypothesis testing problem, we can finally use Fanon's inequality, and we obtain exactly the lower bound that we showed earlier. All right, so this is some lower bound, but we still have problems with this lower bound, right? It lacks any real meaning. Why? Because we have our entire lower bound depends on how we select the set phi. We still did not expect, like right now, the selection is pretty much arbitrary, except for this constraint. So it's hard to get any meaning from this bound. And we also have this mutual information term between a V and the history, where V is the index of the best decision in hindsight from the set phi. So it's also unclear what this term exactly equals to, right? I mean, if this term is very large, then we get here a negative bound, and the bound becomes null. So what we're going to do right now is handle these two terms. All right, so we begin with selecting our set phi. So on one hand, we want to select our set phi to be as large as possible, because then it will yield a tighter bound, right? If I go back a slide here, then selecting a larger k will make our negative term in the lower bound smaller, and thus we'll have a tighter lower bound. On the other hand, we cannot select k to be arbitrarily large as much as we want, because we are also limited, since we must obtain some sort of minimal distance between two stochastic decisions in our set. So this is essentially a packing problem, right? We have some infinite set, and we are trying to fit as many points in the set as possible such that we maintain some minimal distance. So we'll select our set phi to be a packing set. All right. Now this is a more technical part, which I will not go over in detail here. I will be happy to explain this slide in more detail after the talk. But we make this important technical distinction between three different scenarios for the decision set. So if our decision set is finite, then we'll select phi to be a local packing set of the support of the decision set. If the decision set is infinite, but it is still parametric, we'll select it to be a local packing set. And if our decision set is non-parametric, we'll select it to be a regular packing set. So again, this is more technical, and it is not the main focus of the talk, so I'll not go over it in detail. If you want, I can explain it afterwards. All right, now to the second mutual information term. So here we make other assumptions on our metric KL divergence. This part of the paper is also explained in detail in the work by Yang and Behrend from 1999, where they showed the convergence of KL divergence minimax convergence rate. But we need to make the following assumption. So for any two stochastic decisions, P1 and P2, that are close enough to each other in the terms of the metric rho, then we assume that the KL divergence between these two probability measures can be upper bounded by the norm rho squared. This is some regularity assumption on the KL divergence. And when this assumption holds, we can upper bound the mutual information term by 2 times some constant, epsilon squared t. And for non-parametric decision spaces, we use this more general mutual information upper bound. Yes, Chava.
Yeah, if we just finish, but I ask a question after.
No, I finished talking about this slide.
Okay. Yeah. So I'm a little bit confused about this P1 and P2. That I see that like this mutual information term is actually talking about the value of information, or like it relates to what you're observing, right? But then I was also thinking that the policies that you have, like on their own, they don't like interconnected with an environment. They give you, like information, and like you then talk about, the induced distributions given the interconnection of an environment and a policy of the observations, and then you would measure the KL for the observations and not between, like, so now I'm confused, like what is the scale between? Like is this between distributions over observations that are induced by policies in a given environment, or what is the environment? There is no environment here, or like I'm really confused.
Okay, so here maybe I will go back. Here, this mutual information term is essentially the mutual information term here. It depends on the distribution of V. Now, V is some, like the distribution of V is some distribution over points P1 and P2. Now, I will actually show a variation of this statement here later on in the paper, later on in this talk. So maybe then to be more clear, but essentially this part is obtained because we consider a local packing set and not a regular packing set. And also due to this assumption, like it's a technical statement. It uses the fact that the mutual information term here can be upper bounded by t times the maximal KL divergence between 2 points.
Yeah, my question was at a whole different, much more naive level. So maybe I will just pay attention to what comes, because I didn't get any answer. Like I'm really confused about what P1 and P2 are distributions over.
They are distributions over the decisions in our environment.
Yeah, but like then they are not related to observations at all. And I would imagine that what you're observing is going to have a huge influence on how well you can do, right? You have more noise, less noise. Somehow you have to take a suboptimal action to observe interesting things about the optimal action. The informational structure is like, where is that coming up?
Okay, so actually we'll explain about it later. Where exactly is the information coming in? But right now you are correct. Like in this part, and until we finish explaining about the lower bound, the information is not yet highlighted. I will explain it in more detail later on.
Okay, all right.
Okay, so we take this bound of the mutual information term. We also take the previous selection of phi. By combining everything into a singular theorem, we get the following theorem. And what's nice about this theorem is that we have some lower bound here that depends on epsilon, but it actually holds for any positive epsilon that is small enough, depending on the parameters of the problem. And we only need to know the local packing number or the packing number of our decision set. And if we substitute this packing number into this theorem and choose an appropriate value of epsilon, we can essentially get the lower bound pretty easily. So just to clarify it, let's look, for example, at this example for multi-armed bandit problems. So in multi-armed bandit problems, we have a single context and some finite decision set pi. We also know that this mean difference is equal to a constant times the L1 norm between two stochastic decisions, where here the L1 norm is like the find psi or some vector is some vector in the probability simplex, and this is simply the L1 norm between these two vectors. Then the log packing number can be upper bounded by the cardinality of the decision set -1. If we substitute this into our lower bound here, we get this expression. And by choosing this value of epsilon, which maximizes the lower bound here, we get that the Bayesian regret is bigger than up to some constant from square root of the cardinality of pi -1 times t, which is exactly the well-known lower bound for multi-armed bandit problems. Yeah.
So I'm a little confused by this example here, because here you say that the metric that you choose is the L1 distance, but is this assumption that you showed previously on the KL, on like 2 slides ago, right? That says that the KL should be upper bounded in terms of the square of this metric. So is this ever satisfied for the L1 distance?
Yeah. So just note that the assumption here, it assumes that there exists some epsilon 0, such that for two decisions that close enough, this holds. And this holds for the L1 distance from the reverse spin squares inequality. So it states that the KL divergence can be upper bounded by some constant times the L1 norm.
Right, okay, but I guess that constant is going to depend on epsilon 0.
Yeah.
And can you show where this epsilon 0 shows up in the example?
So it does not show, it is not explicitly shown in the example, but the assumption here is, again, because it's a slide and I wanted to be more precise with less details, but here epsilon, the positive epsilon here needs to be smaller than epsilon 0 as well. Okay.
So, but that eventually means that a bar also depends on epsilon, no?
Wait, the constant here, a bar, yeah.
So
okay, I see what you mean. I see what you mean here. Okay, I think I need to make sure. I need to make sure of the smaller details here. But a bar, I think, should go like 1 over epsilon 0, something like that.
Right.
Yeah. Yeah, I think that. Yeah.
Okay.
Yes, Chava.
I'm confused about the C bar thing. So if I have a reward structure and all the rewards are going to 0, then the difference between the performance of the policies goes to 0. So C bar could be arbitrarily close to 0, depending on how I choose the rewards. So does it mean that like there is no row, or like what is that saving us? Like some normalization here is happening, and like without loss of generality, we can assume that this is not happening. What's happening?
So actually, this is one of the reasons we chose a local packing number. So a local packing number is essentially the largest packing number. When we try to pack a sphere with radius epsilon, yeah.
Sure, but you had the assumption on rho.
Right. Which assumption are you referring to?
First assumption that was mentioned in the talk about rho.
Yeah.
That was the assumption that it's lower bounding the performance difference between policies. Right. And that seems to be not true. Just if the rewards are big enough or something like that, right? Like it doesn't hold uniformly. So I'm confused about that. I guess like maybe you're saying that like you want for any reward in the vicinity of that reward, that assumption to be satisfied, and then you're good. Like that's what you're talking about. Is that how it works?
Wait, I don't understand why does the assumption does not hold here. Why? Because
It's
the rewards
because,
can be.
yeah, like all the rewards go to 0, then like the album metric is not going to lower bound the reward difference, which is 0, and the album metric is positive, so it's not a lower bound, like with any constant. So
Now all right. So here, I think we make the assumption that the rewards must be different, right? If this is equal to some constant or lower bound, but some constant times the L1 norm, we must have
like,
the.
Yeah, 5 slides ago, there was this assumption about the row.
Yeah.
And I think that there you probably want to say that like you fix any reward and in the vicinity of that reward, that assumption needs to hold or something like that. Or like for some subset of the problems.
I think I mentioned it earlier, but yeah, it's for some subset of the problems. You only need this assumption to hold for a subset of the problems because you can still lower bound the regret using the subset of the problems.
Right. Got it. Okay, so then I was missing that point. Yeah, sorry about that. Yeah,
it's okay.
No, I see. It's like you would take the critical set of problems as usual, where there is some gap in the rewards, and like, okay, so then the rewards are not arbitrarily small. Okay.
Yeah.
Got it. All right. Interesting.
Okay. So I go to in the full version of the paper, you can see that we also repeated this process for some other online problems, tabular reinforcement learning, linear bandits, and Lipschitz bandits. So we also have that. All right. Okay. So really up until this point, we did not highlight anything about the information. Like if you remember at the beginning, I told you we look at the trade-off between regret and information. But up until this point, we obtained the general Bayesian regret lower bounds. So now we start talking about this constraint. Mainly, we ask ourselves, how does the regret change when the number of bits of information is constrained? All right. So from this point onwards, we will only consider finite decision sets, and we will denote the cardinality of the decision set with K. Now, from information theory literature, we also know that the mutual information between pi star, which is the optimal decision, and the history measures how much information the history has on pi star in bits of information. Now, for this because we apply to general algorithms, we will use the KL divergence between the agent's policy and the prior to measure the accumulated information the agent has. And then we will look at the following constraint. We look at the worst case regret under this constraint on the agent's policy. Okay. So this is what we're looking at. So our goal is to use our method to obtain lower bounds that depend on R. And in order to achieve this, we need to rethink exactly how we are choosing phi and how we will upper bound this mutual information term here. All right. So we are going to select phi to be the same as before. And since we have a finite pi, we know that we need to consider some local packing set of it, which we'll denote by E. Now let's look, since we have some specific prior P of pi star, we will look at E tilde here to be E after applying our constraint of KL divergence. We also know that this mutual information term here can be upper bounded by T times the possible maximal KL divergence in our set. Now, why exactly is that? This is because you can decompose the mutual information term and write it as sum of T KL divergences. All right. From a scaling underment of the information radius, we can upper bound this maximal KL divergence by R divided by log K times the maximal KL divergence without the constraint. And our final step is by regularity, and since E is a local packing, we can upper bound the maximal KL divergence in this set by 2 times A bar, which is our constant from our previous assumption, by epsilon squared, since epsilon squared upper bounds the norm row between any two decisions in our local packing set. All right. If we combine our selection of phi with, if we combine everything in this slide, we can combine it to this simple proposition. So let the previously mentioned regularity assumptions hold, and let R be between 0 and log K be given. So when the cardinality set is finite, under this constraint of the KL divergence, the mutual information term can be upper bounded by this expression. All right. Now, if we substitute this mutual information term bound into the Fano-like lower bound that we previously proved, then we obtain this following lower bound, which is essentially exactly the same lower bound, except this time, instead of 2 times A bar epsilon squared T, we multiply it by also this term here, R divided by log K. All right. Now, what this term here allows us to, now you can actually see it from here. If it's exactly the same form, except here we multiply epsilon squared by square root of R divided by log K, we expect that our lower bound now will have some term of square root log K divided by R added to them. And this is actually exactly what we see for multi-armed bandits. So if R is positive, then for multi-armed bandit with K arms, we have this lower bound here, square root of TK times log K divided by R. So it's essentially the optimal lower bound, except to multiply it by a square root of log K divided by R. And furthermore, if R is equal to 0, then we have linear regret. All right. Okay, so due to the shortage of time, I will not go over the proof, but the proof for both positive R and R equals 0 are actually quite simple and straightforward. So I will not go over them. We also showed this regret upper bound for a K multi-armed bandit problem with the constraint that we have accumulated exactly R bits of information by the end of our exploration. So for a K multi-armed bandit problem with R bits of information accumulated, there is an algorithm whose regret can be upper bounded by this term here, O of log K square root of KT divided by R. Okay. So the proof idea here is actually to, instead of thinking about it as a constraint, we instead say that we have some two versions of our observations, OT and the modified version. And we assume that for the non-modified observations, there is no constraint. It's regular observations. But if we have modified observations, then we have this constraint. And then we examine the regret of Thompson sampling, just simply updating the posterior distribution instead of with the non-modified observations, with the modified observations. Again, I will not go over the proof here, but essentially we we analyze the information ratios of Thompson sampling with and without the modified observations. And then we use this with the existing literature that studied the information ratios. Wait, can I finish this line? That to upper bound the Bayesian regret for the algorithm with the modified observations, which essentially concludes our proof. All right, now before I go over to the next slide, I saw that someone asked the question in the chat. All right, so Chao, you asked, the history depends on the algorithm. What does assuming a bandit problem with mutual information? All right, so what it essentially means is that the following. You can think about the history, or you can think about the algorithm. Let's say you run a bandit algorithm for T steps. Now the algorithm can leave some distribution over all the possible histories that you have accumulated, right? So essentially, our algorithm together with the environment defines some measure over all possible histories. And then you take the mutual information of the optimal policy with this unknown history distribution. This is what it means. All right. I hope I've answered you.
I think I have a very similar question.
Yes.
This, I'm still not sure I'm understanding this argument. So you're saying that let's assume that this mutual information is equal to R, right? And then what do you mean by the implication that there exists an algorithm with regret upper bounded by this? It seems like a little bit circular for me, this reasoning that assume that the history satisfies this equality, and then there exists an algorithm.
Okay.
So
Okay.
how do you untangle this?
Okay, no, I see. Now I understand better what the problem is. So, how can I better explain it?
So maybe it's rather that there exists an algorithm such that the mutual information between the history and pi star is equal to R, and the algorithm achieves a regret of the order root
it's
T
both of them
over R.
Yeah, maybe I need to explain it better, but yeah, it's actually what you said. It's both of them. There exists an algorithm such that it is equal to R, which again is done via the modified observations, and the regret is upper bounded by this term. Yeah.
Okay.
Okay.
Sounds more reasonable. I'm not sure if Chao is satisfied with this, but they can just type in the chat.
Yeah.
And you can just go on.
Yeah, I see another question. Yeah. We can't hear you. Okay, we'll go on, and you can type it in the chat, or maybe if your microphone will work. All right. So now if we combine both bounds, we can actually quantify the trade-off between regret and information. Okay, so let's say our original goal was to find some method where we can trade off between regret and bits. Like say we have some agent that has accumulated a certain amount of regret. Can we quantify it in terms of how much bits of information we need to achieve the same level of regret? So, well, we did not achieve an exact relationship between regret and bits. This is because we have some suboptimality between our lower bound and upper bounds of square root of log k. Still, the regret upper and lower bounds can give us some range of valid values that we can have, right? So for example, if we take the lower and upper bounds and we substitute, for example, say r equals 5 bits, and we know our t, our highs, and the number of arms in our problem, then we can get a valid range of regrets that we can say, okay, this number of bits is equivalent to regret between this value and this value. All right, so while we don't have an exact answer of 5 bits in this environment is equal to this amount of regret, we still have some sort of estimate as to how many bits is equal how much in terms of regret. Right, I also saw another question in the chat. So thanks for, so yeah, Chao, our algorithm, so we fix an algorithm first. It means that we have some sort of bandit algorithm, yeah. Yeah, we fix an algorithm first, and the mutual information here between the optimal policy and the history is the mean mutual information. We do not look at one specific run. It's like looking at the average regret. Okay, so Chao asked if I'm proving the worst case. So Chao asked if I'm proving the worst case Bayesian regret for any algorithm. So the lower bound holds for any algorithm, right? And the upper bound is for this specific algorithm with these specific modified observations such that the mutual information constraint holds. I will just go over, like I still have a couple of slides left, and then I will go over the questions in more detail. I just don't want to take a lot of from everyone's time. Okay, so now I will briefly discuss the experimental setting. So in our experiment setting, we have one main experiment, which is the bits with the large language models. So as I'm sure all of you know, large language models are a family of text generative models where we input some prompt to the language model and we receive some distribution over all possible next tokens. Now, in our problem, we are interested in the following problem. Let's say that we have many multiple choice questions, which we must answer using one of two available LLMs. One model has few parameters, and another one has significantly more parameters. Now, since we have some finite compute resources, we can use the LLM with less parameters pretty much freely. It does not require a lot of resources. But for using the one with more parameters, we suffer some small penalty. We also know that we receive a relatively large positive reward for answering a question correctly. And we then ask ourselves, how should we select the large language model? Right? So briefly, our idea is the following. Since we can use this small model pretty much freely, we can use its output distribution to measure how much information it has in bits. This is done pretty simply by using the KL divergence. And we also know that if we have less bits on a problem, we can suffer more regret. So we should accumulate more information. So the idea here is to set some threshold of value in order to make a decision rule such that we will know which LLM to use. And then we use, for example, if we have very few bits, then we know, okay, we should query the large LLM. If we have more bits, then we'll say, okay, we should avoid paying the penalty and avoid suffering the penalty, and we can still receive a positive reward. Right? So this is just some technical statements. These are just the results. So in all of our experiments, all of the settings, like with all different combinations of large language models, pretty much always the bits-based decision rule, be it the random decision rule, really showcasing the potential that using bits in a decision-making setting can have to realistically improve performance. We also did some basic toy experiments using a simple Bayesian multi-arm bandit environment, where we compared the rate of information accumulation of 3 different bandit algorithms and looked at how it affects regret. So I think the results here are pretty much expected. Algorithms like EXP3 that accumulate less information also suffer additional regret. On the other hand, Thompson sampling, which is very good at accumulating information from the environment, also suffers less regret, and its regret decays much more quickly than other algorithms. This is just some additional pretty simple result that we also showed in our paper. We also looked at the lower bound that depends on the prior's entropy, and we managed to obtain the following lower bound, which also almost nearly matches the lower bound for Thompson sampling, the upper bound for Thompson sampling, which is a pretty well-known result. Right, so to summarize, we began by introducing a novel method for obtaining regret lower bounds and applying it to existing well-known settings. We then looked at the bounds that depend on the number of bits of information an agent has. So we proved the lower bound, we proved the nearly matching upper bound, and we demonstrated the utility of these 2 bounds to explain the information regret trade-off, and then showed how it can be used to improve performance using bits. All right, this is also some other interesting topics, future work, using bits to improve decision making in more complicated reinforcement learning settings. From a more theoretical standpoint, you can think about how to extend the definition of bits to other non-Bayesian settings, for example, adversarial setting, and see if we have some sort of a similar trade-off in those settings as well. And also from an algorithmic theoretic standpoint, think about how we can query information in the adaptive matter to improve regret in general agents. Right? And that's it for my talk. Thank you all for listening. And if you have any questions, feel free to ask me.
All right, very nice. Thank you. So I guess I'm still processing in my head this main result. I guess like both upper and lower bound wise, like the role of R. So you're speaking of R as the mutual information between pi star and the interaction history, right?
Yeah.
So which is essentially the number of bits of information that the interaction history captures about pi star.
Mm-hmm.
But what I sort of struggle to understand, maybe I have like the wrong units in my mind. So imagine that I have like an interaction history that captures 1 bit of information about pi star. So then the upper and lower bound are exactly the same as what you get for the standard bandit setting. Is that right?
No.
Okay,
for R equals 1.
Right.
If you put here R equals 1, you get square root of tk log k. You have this additional square root of log k factor.
Okay, right.
If you put R equals log k, actually, you get like R equals log k is without any constraint, so it is reduced to the regular lower bounds and upper bounds.
Right. I see. Because the optimal action is of course encoded by log k bits.
Yeah.
So if you have an interaction that perfectly reveals that, then
actually it can be interesting. Yeah.
Yes, I'm saying that. Okay, so imagine that R is log k, right? Which means that the interaction history fully captures pi star. Imagining that, of course, like pi star is uniformly distributed.
Like R equals log k, you are saying?
Yeah, let's say.
Like this is the regular setting, because in the regular setting, like of course, assuming that you have like no special constraints, because then they will be in the mutual information term. But in the best case scenario, for like the optimal, for the exists algorithms such that the mutual information term is unbounded for general T. Now I'm going to be careful here by saying that, because like you have this general omega of square root of tk, but of course you can maybe think about and devise some like show that for any algorithm, like in the worst case bandit problem, after I don't know, let's say t equals 2000 steps, you have at most r equals to log k minus some epsilon, and then you can substitute it here, but this epsilon will go to 0. Like maybe you can say this. Yeah. And actually, it can be interesting to think about when you have both constraints. So like, you know that the optimal policy can be represented by less than log k bits. And then you have at most r bits, which is less than the required number of bits. I did not look into this, but it can also be interesting. Yes, Chava.
So regarding this lower bound, so I understand R is at most log k, right? Is that a lower bound on how small r can be?
It has to be strictly positive.
Yeah, but like there is no other bound on it?
No.
There must be, right? Because otherwise the lower bound could be arbitrarily improved.
The lower bound can be improved. It will be arbitrarily
large, right? I can make the lower bound to be large if r goes to 0.
Yeah, for r equals 0, the lower bound is actually linear. Now, there is no bound in terms of how small R can be, but if I will go back a couple of slides here, then where is it? Oh, wait, no, sorry, I went forward instead of backwards. Here to here. All right, so again, there is an implicit assumption here that I did not write just to be concise in our slides, but epsilon must be smaller than some constant epsilon 0.
Okay.
Right? And if we look here, for our selection of epsilon, we choose epsilon that goes like square root of 1 over r.
Okay.
Okay, and this has to be smaller than epsilon 0.
Right.
Then, yeah, it essentially increases the valid values of t, from which point the lower bound holds.
Yeah. So there is no contradiction in a way, because like I can choose a policy that doesn't reveal any information about the pi star, or like it reveals minimum information about pi star. I don't know how to do that, but maybe stick to one action or something. And then you would think that, okay, like then the lower bound becomes really big, but we know that the Bayesian regret for this KM bandits should be square root KT, lower bound, upper bound, basically the same, right? So I was trying to understand how this is avoided, but I see it now. Okay. I guess it's this information structure where, you know, like all of this could be more interesting in non-standard bandits, where, I don't know, like somehow, you know, choosing one arm gives you more information than the others, maybe heteroscedastic, or like there are many versions of this, right? And then this, like the relationship between information and regret is not as simple as in the standard bandit setting. So then you can learn about the information structure, like the value of information, a little bit more.
Yeah, actually, it's one question that also me and my advisor thought about, is looking at bandits with a graph feedback, where like you have actions, that one action reveals information about the actions which are connected to it in the graph. Like, I think like this is, of course, a very, like, I enjoyed working on this work. It was also accepted to iClear, but it's very preliminary, like in its ideas. I think that a lot of additional work can be done in like studying the dynamics of an agent and how, like, if, for example, we have some MDP, then we have some area that has a lot of information, but we suffer a lot of regret for exploring in it. And another area where we do not study a lot, but it has very high reward. So how exactly an agent behaves to optimally trade off between these two different areas. So stuff like that, I think, are very interesting.
Yeah.
So I guess like following up on this last thought, so like what do you see as a relation between this idea and like information ratio type analysis and information directed sampling? Like, I mean, I can see like several possible like vague connections, and you did mention that you use some information ratio arguments in your analysis, but like how does this analysis in your mind shed new light on this algorithm? I'm just really curious.
So I think the main, like for these specific algorithms, so I mainly talked about external information as our main motivation, but R here is like the general mutual information between the accumulated history and the policy. So it becomes more relevant when you talk about the rate of information accumulation, like how quickly can we collect bits from our environment. And this is actually in the last experiment, I think I looked at some algorithms. I looked at Thompson sampling, approximate posterior sampling, and EXP3, where it's like I simply ran the simulation across a lot of bandit seeds, and calculated the mutual information and the regret. So I think this is one aspect this trade-off highlights, like trade-off between the rate that you accumulate bits from the environments and the total regret that you suffer.
Yeah. I guess my question wasn't super clear, but I guess like what I'm thinking is that this quantity, this mutual information between the history and pi star. So this is precisely the quantity that shows up in an information ratio analysis as well.
Right. Information ratio analysis is the conditional mutual information, right?
Right. Yeah, but it eventually telescopes to this term, right?
Yeah.
So that's like essentially in the last step in that proof that you say that, okay, never mind, the sum of these conditional mutual informations is precisely this quantity. So then I'm wondering, like, what does this say about your upper bound, for example?
Oh, that's so.
Like, for example, if you
technical.
just simply assume that this mutual information term is upper bounded by R, then what do you get from that analysis?
So what I also looked at the analysis of like the original and other analysis that use the information ratio to upper bounded regret for algorithms that use the posterior sampling, Thompson sampling. And like in their analysis, the upper bound of the information ratio really heavily relies on the fact that you use exactly posterior sampling from the rewards that you receive to upper bound the mutual information term. Now, like due to time shortage, I really went over it briefly, but we see that for the modified mutual information that it does not, like if rho t is the information ratio of regular Thompson sampling, then when you have this constraint, the worst case mutual information ratio can be upper bounded by R divided by log K times the regular information ratio. And then I can use the standard results to upper bound this information ratio here.
Right. So maybe can you say a few words about what these modified observations actually are?
All right. So these modified observations are actually, like, I did not really calculate it exactly, but they do exist because you can construct them in this manner. And you can construct them in this manner that this upper bound holds essentially. Like you can choose because you have some modified observations, there exists some, let's say, information channel here, a compressor, for example, that you can compress these results such that these constraints hold. And you have Thompson sampling to behave in a way that you want.
I see. So basically you compress the observations and then you use that to update your posterior and do Thompson sampling on top of that.
Yes.
But yeah, I guess like the details of that compression are not very easy to explain.
I mean, you don't even need to explain them because you only need the compression to exist.
Yeah, but I guess if you want to run this algorithm, then
yeah.
I guess it's still need to
be
able to
if you want to run this, yeah, but then why would you run this algorithm on modified observations if you have the real ones? Only if you have some like storage problem.
Yeah. Oh, got
it. Okay, wait, I see. Never mind. I see, Chow, that you asked. You sent me a paper link in open review. Now I don't think I can view it right now. Maybe I can. I will stop my presentation for now. Here, right. And I will open this 1 second. I will open what you sent me here. Here, yeah. Yeah, actually, I saw this paper as well. For a general characterization for bandit learnability. I actually saw another paper also by the same group with Foster Achlin, like the complexity of adversarial decision making, I think this paper is called. this is like a continuation for this work. They actually apply similar methods, like similar in idea, but not in the exact technique. They actually use their own term, the DEC, the decision estimation coefficient here, which is essentially the regret with some divergence regularization. And then they say, okay, change the divergence, you can change the DEC. Now, I don't think that they use packing and covering to obtain the lower bounds. So this is like one difference. But I actually didn't really get into this paper again, only the previous one. But I will read through it more thoroughly. Like there are also other papers that use some variation of funnels inequality to work on regret. But like they used the pretty much, except for using funnels inequality, the technique was actually pretty different than mine. Are there any other questions?
Sorry, I've missed the recording. No.